first organic lectures with me. So I'm going to give you 6 lectures on reactive intermediates. So this course is composed of 4 6-lecture blocks. Okay, first 6 from me. Everyone see? Then there's 4 from Dr. Wallace. And Dr. Bedford. And then Professor Flitch. So any questions about exam format, etc., etc.? Professor Flitch is the course convener. And she'll be lecturing at the end. So, lectures 6 on what's called reactive intermediates. So mine's covering all sorts of different bits of chemistry, mostly on radicals. So lectures 1 to 6. If anyone wants to get in contact with me, do email me. That's my email address. Whitehead@Manchester. I have a fairly open door policy, so if you email me, I'll arrange to see you at any time. And there are 3 principal texts courses Clayman. A particularly useful text is the Reactive Intermediates Primer by William Wotton, and if you want more details, then possibly by Parsons is very useful. So, we're going to be talking about reactive intermediates.
Will's got a lecturer called Dr. Moriarty, who obviously isn't a professor for
So
that reason.
quite warning, this lecture course used to be 8 lectures up till 2 years ago. It is now 6. The only exam questions from more than last year ago aren't necessarily reflective of the current course, because we've lost 2 lectures. Most of the course is the same, but there aren't, not everything the same as it was 2 years ago. So I'm going to be talking about neutral reactive intermediates and focusing on radicals, what they are, their structure, their stability, their history, how you make them, and then how we apply them in synthesis. And the whole idea of this course is that you learn the basics of radical chemistry, and then we carry out lots of problem solving in terms of working out what's happening in radical reactions. The first lecture is very much an introduction to the background of radicals. I think it's filling the gap type approach. So most of the writing is over there, and I can put in pictures. So we're looking at organic reactions which go through reactive intermediates. Let's just consider a simple transformation. It's very much revision of the starting material. That's an intermediate going to a product. Fairly common process. Of an equilibrium, the formation of intermediates, and have essentially irreversible formation of products. We'll put some K's on there. K1, K minus 1, and K2. So that intermediate is called reactive. So I is reactive when K2 is very much greater than K1, i.e. it destroys the multiple quicker than its form. So destruction far faster than formation. We've seen a few of these sorts of processes, and they will have a fairly common reaction profile. So we can go back to kinetic thermodynamics. So So for any reaction, we've got a reaction profile, we've got free energy in that direction. I've got progress of reaction. In that direction. So we start off with our starting material. The reaction's going to go towards the products. We hope the products we've given our equation so far. Our intermediate sits way up higher in energy than both. There's our reactive intermediate. We go way up. We get to it, and we'll fall over the cliff away from it. That's a typical energy profile for a reaction proceeding to a reactive intermediate. Right, I've asked questions in the past about various definitions on this curve. Let's just remind ourselves what the two peaks are called. What are the two peaks on the curve called?
Transition state.
Transition state, brilliant. That's TS1, first step, TS2, second step. There are also associated activation energies. Now, any more? Okay, so the first activation energy, step one is that one, and the second one, and that one. And that proves why we've got such a reactive intermediate, because the EA2 is so much less than EA1. Anybody remind me of the equation that relates activation energy and rate constants? Names? Arrhenius? Technically. Anyone?
A to the minus EA over KT. Or
RT. Brilliant. So there's an inverse relationship in activation energy, isn't there? So the smaller the activation energy, the bigger K. Arrhenius. So that's a classic example of a reactive intermediate profile. Now, we've met quite a few reactive intermediates in the early years of the course, and quite often they're charged. So you've done SN1 reactions, for example, where you make a carbocation, and they're high energy species. Got some simple charged ones, and the whole point of my teaching is to try and remind you of your chemistry that hopefully hasn't gone from your memories. So let's look at an electrophilic aromatic substitution reaction. Here's an aromatic ring. Benzene. This is benzene. Very stable. Yes, it's an electrophile. Electrons given from the benzene ring. It's an electrophile to give us a charged species. That is now a cation of various resonance forms, and that is the Wheeler intermediate. That clearly is far, far less stable than start material. We started off with an aromatic system. Aromatic systems are very stable. 6 pi electrons, 4 n plus 2 in a cyclic array. Very stable. Stable. Way of energy. Want to get back to stable. So to get back to stable, we lose H plus. Substitution. seen many things like this. That's just a classic example of a reaction intermediate. The Williams intermediate, very high energy, particularly compared to the very stable two which is either by the side of it. Again, in terms of the reaction profile, I tend to pull off the bottom of the screen, so don't mind me if you can't see anything. Start off with our benzene and E plus. We're going to go to our product H plus, low energy, and we go up. Williams medium, and then down again. So W I. So the intermediate is the trough that peaks are the conscious states. The energy. Progress. Right, so that's a pure reminder of first year, second semester, chemistry, and one year of reactive intermediates form slowly, react quickly. We're not really interested in these in this course. We're more interested in what are usually neutral and electron deficient reactive intermediates. So these are the focus of this course. And I'm aware that some of you are working on some of these in your M-Chem projects that you do it. So the species that contains carbon at the active centre can be trivalent with a single non-bonding electron. And those are carbon-centred radicals. And that is going to be the main focus of the 6 lectures. We're going to look at ladder. They can be divalent with 2 non-bonding electrons. Who wants to tell me what a divalent carbon with 2 non-bonding electrons is? Carbene, thank you. I believe you've met those in inorganic chemistry. And they're attached to metals, rocks, and those are radicals and carbenes. They are both highly reactive species. And stabilizing somewhere. And why is that? Well, for a radical, very simple. And that is simple carbon-centered radical. It's only got 7 electrons in its valence shell. Not happy. That's not good. Let's get 8. Carbenes. We've got even less electrons in the valence shell. We've only got 6. Both of these are particularly reactive because they want to regain their stable octet. Very simple. Okay, so we're not just dealing with carbon, we can also deal with other atoms, and nitrogen species can have 1 electron as well. So we can have a divalent nitrogen with 3 non-bonding electrons. Called an aminion radical. And it can be univalent with 4 non-bonding electrons. Anyone know that's good? And like carbene, but in nitrene. Then aminion radical. Divalent nitrogen. Lone pair. 1 lone paired electron. So again, 7 valence electrons. Reacted. And the nitrine. Nitrogen version of carbene. 2, 4, 6 valence electrons reacted. Examples of useful, very useful synthetically radical species which are very high in terms of their activity. One other type I want to mention from a historical point of view are something called arines, and if you look at the primer I mentioned, it's been discussed in quite a lot of detail in that primer. And these are things such as benzene. I like to mention these because they behave a bit like radical species. Now, benzene is an unfeasible structure. If you draw it where it's generally drawn, that is a structure often drawn as benzene. Can't be. You can't have sp hybridized centers and they sit under grace. That's a formal representation of benzene, but it actually looks like benzene. 2 sp2 orbitals, either with an electron in each, or 2 in one and 1 in the other. That's a formal representation of benzene. That is not a full bond. 2 sp2 orbitals adjacent to each other. And 3D, what that looks like. sp2 orbitals orthogonal to the pi system. Maybe perhaps not met, as I showed before. Those 2 electrons are not involved in the pi system, and they are very reactive species. They want to get 4 octets and haven't got them. Then they are related to radicals and carbene. So that's an introduction. Reactive intermediates, way up in energy, totally slow formation, very rapid disappearance. Now the problem with species like this, of course, is very reactive things are usually very hard to tame in terms of synthesis. So, 100 years ago or so, it was never believed to use radical reactions in synthesis. But it's a massive area of chemistry. It can be done if you're careful. So I'm going to focus specifically on radical chemistry. It's the most useful in terms of organic synthesis, and it has quite a lot of biological relevance as well. So what is a radical? An atom or molecule which possesses at least 1 unpaired electron. At least 1 unpaired electron. Nearly neutral ones we're interested in. You do get some charged ones, but mostly they're neutral. And I'm giving you a selection of these underneath. Chlorine, bromine, oxygen centered, sulfur centered. Now, even though they're neutral, they do possess a degree of reactivity in terms of being electrophilic and neutrophilic. And we'll come back to that later. Those ones I've got on screen now are all electrophilic radicals. They tend to react in their chemistry with more electron-rich species. So these are electrical chemicals. And we'll use terms to describe these quite often. Those first two are halo radicals, and alkoxy radical, hydroalkyl, haloalkyl, alpha acyl. Acyl group is alpha to radical centre. And again, we don't draw the lone pairs all the time. We're only interested in terms of chemistry. It's a single electron, so we draw that as Cl dot, Cl dot, O dot, S dot. I'm not concerned about the lone pairs, I'm concerned about that single unpaired electron which wants to do something basic test. So those are electrophilic radicals, and we'll see a few of those, many of those actually, in the next few weeks. And those three at the bottom are nucleophilic. They tend to react with electron deficient species. Again, I'll explain that further later on. Alkyl, alkoxyalkyl, and acyl, where the radical is actually on the acyl carbon. Here's a typical example of radicals you can use, or you will see being used quite extensively, synthetically, usefully. They're all neutral. Charged radicals. Well, you can make charged radicals. And again, working very synthetically useful reactions which make charged radicals. You do any organic chemistry with amines. You'll often find they're coloured. And the reason they're coloured is because amines tend to lose electrons quite easily. So an amine is able to lose an electron. If it's got somewhere to go. Now, from past experience, people have difficulty drawing arrows with that chemistry. So I'm going to put a minus electron here. The electron I'm going to take is one of those lone pair electrons. So that's our lone pair electron. I'm going to take that electron away, and as you'll see later, we only ever use fishhook arrows, or we're taking electrons away or giving to things. So we'll take an electron away from that nitrogen, and do that, it becomes positive. And that's a radical cation. So you can lose electrons from amines quite easily. That means they can reduce things. They're in fact mild reducing agents, amines. Let's give electrons away. Okay, that's science. And that's what gives you your colour quite often when you've got a reaction involving an amine. So that's a common, in fact the best reducing agent in nature is NADH, it's an amine. Take an electron away. That's a good example of it. Okay, we can also give electrons to conjugate systems. We've got a naphthalene down there. So highly conjugated systems can accept electrons. Accept electrons. And we should invent a reaction which involves this, which is actually discovered in our department. So, give an electron source, you can give an electron to our aromatic ring system. And the way to think about this is to take one electron from the formal pi bond and pair it up with the electron we're giving. And take one electron from the pi bond and locate it on the adjacent carbon. That gives us a radical anion. Got one electron located on the carbon, we've got electrons paired up on that carbon. That is a reduction of the aromatic ring by an electron, a radical anion. Anyone know a reaction that proceeds via that mechanism? Metallic sodium, ammonia. We will do next time. I've got a question for you again, let's go. Radical anion. Okay. So most are neutral, you can get positive ones. Right, so as organic chemists and biologists, for that matter, why are we interested in free radicals? Well, they are reactive. They've usually got an odd number of electrons, and they want to fill their shell, and they participate in homolytic processes. Now, something that people go on every year is that they only really do two sorts of reactions. They abstract things, and they add things. You don't do a substitution reaction directly, like an SN2 reaction, you abstract something. So if I've got a radical R, and the species XY, I can abstract X from XY, leaving Y dot behind. So one electron from R, an electron from single bond, and an electron from Y. That's an abstraction. That's X and XY. Other types of reaction. Abstraction, that's one. And addition. That reaction will be reductive if the RX bond is stronger than the XY bond. What we'll see in lecture 5 is that perhaps the most useful reaction in radicals is addition to alkenes, where we take an electron, make a bond, form a new bond. Again, an alkene. Now we add that alkene, forming a new bond with the left-hand carbon, and relocating an electron onto the right-hand carbon. An addition reaction. Those are the two principal types of reactions that radicals undergo in synthetic chemical reactions: abstraction and addition. Don't forget that, because people come to SN2 reactions with radicals and you can't. Abstract things. So, way back in 1906, a chap called Bomberg realised how good radicals were. He couldn't actually make use of them. So they realised that their high reactivity, they lack of selectivity. Radicals are a bit like a bull and shiner shop. They don't really care what they smash. Just run around getting anything. So we need to find a way of controlling that behaviour. So they're short-lived species, making them go on all sorts of undesired processes which you don't want to happen. So some of the reactions they undergo that are undesired, they can combine with themselves, so they can dimerise. We don't want to make dimers particularly. We have two radicals, they collide, they will form that octet like clappers, so very, very quickly form a CC bond. So that's the first point. We don't want radical concentration to be very high, else we'll get reactions between them. So all things are wrong, we'll find out about chain reactions and we keep the concentrations low. And we'll see that next time. They can also disproportionate. And you'll know what disproportionation means. Anybody? Good. Spontaneous oxidation and reduction of the same species. Spontaneous oxidation and reduction. So there we are, I've got two molecules of the same thing at the bottom, and that can undergo disproportionation. So we can add a hydrogen to one of those species, that's the reduced form. We can lose an H with one to the oxidized form. That is simply disproportionation. And in fact it's nothing fancy, because all we're doing is an abstraction reaction. What I'm doing is taking that radical, taking away that hydrogen, that is my reduced left-hand side, remaining electron, then pairs up, giving me an oxidized species. So this proportionation is simply an abstraction process. So again, it involves two radical species bashing into each other for it to take place. The key point here, we don't want high concentrations of radical species if we want to control them. Okay. Who remembers their first year, first semester chemistry? Yeah? Who remembers their first year, first semester chemistry?
Nope.
Yes?
Ready for the exam, don't know.
Oxygen. Oxygen is the enemy in radical chemistry. So if we do radical reactions, we don't want high concentrations, we don't want air anywhere near them. So let's look at oxygen. O2. It's a reactive gas. Oxygen is 1F2, 2F2, 2P4. Professor McInnes's lectures, I think, in first semester, hopefully. You can draw an MO picture for oxygen. Bring in Dale first, there we go.
1 and 3. It's not enough to.
2 sets of atomic orbitals on oxygen. 1F2, 2F2, 2P4.
Only when I'm on.
One-s orbitals, not particularly well because they're buried. We get a bit of bonding interaction down there. 2 S's interact bit better. And the two P's interact. Even better. And that's what the MO diagram for oxygen looks like in terms of energy levels. There are a total of 16 electrons to fill. 2, 4, 6, 8, 10, 12, 14, 16. So the key thing about oxygen is its para or diamagnetic? Para. Thank you. Good. Paramagnetic, 2 unpaired electrons. It's biradical, formally. That's why it's the enemy when it comes to doing radical chemistry. You don't want something that's got available electrons around unpaired, but wants to become paired. So a useful way of thinking about oxygen from an organic chemistry point of view is as so. I don't think our inorganic colleagues should perhaps be that much of a fan of that presentation, but it helps you understand why it's dodgy for organic chemistry. Diradical. Therefore, if you've got oxygen in your reaction involving radicals, they will die because O2 is highly reactive towards radical species and you form peroxyradicals very, very quickly. Simply by combining R dot to form O2. Peroxyradical. So oxygen is the enemy. High concentrations are the enemy. Solvent is the enemy. With some solvents, because radicals being very reactive can react with certain solvents. And certain solvents are an absolute no-no when it comes to radical reactions, in particular ethereal solvents. You can't use ethereal solvents. So what ethereal solvents do you all use in lab? Ethyl ether. You do not do radical reactions in ethyl ether, because it reacts very quickly. I'll explain why next week, or next time, sorry. But it can very easily abstract the hydrogen and the carbon next to oxygen. But if you go into radical in ether, it's going to die. Because it abstracts the hydrogen and the carbon adjacent to oxygen. Alright. The other ethereal solvents you're aware of, bromine and CAM group, BPAs.
Trodium ether?
No, that's got just CH bonds in it.
CHF?
CHF. CHF is just a cyclic version of ethyl ether, where you link some your carbons together. That's CHF. You can abstract the hydrogen atom the same way as you can on ethyl ether, which is not a desirable process. So, oxygen is dangerous during our success. high concentrations, radicals are dangerous, you get diamondization and things like that. Strong causes solveness. So we are very limited in what we can do. Careful choice of reaction conditions, etc. Okay, despite this, it's a huge area of research. So, last 40 years, a huge number of reactions and radical intermediates are obtained and used in large-scale reactions, even on process in industrial environments. And the reason for this is because there's a lot of advantages to using them, apart from those just discussed. First of all, you can functionalise CH bonds, simple alkyl CH bonds. You can't do that with anionic or cationic chemistry very easily. So you can functionalise all reactive status, match up the CH bonds. You haven't got to protect a lot of functional groups, not only got to protect the group because it becomes nucleophilic or electrophilic, you haven't got to protect OH bonds, NH bonds, carbonyls. You leave them as they are, and they won't become affected when reacted. So, some of you will know that one of my pet's favourite things is VPAs. My second pet's favourite thing in radical chemistry is bond strengths. So bond strengths are very important in radical chemistry. So just to give you a feel of bond strengths. For example, CBr bond is a relatively weak bond. Yeah? 285 kilojoules per mole. You have to know these. So that's a weak bond. That one could well become involved in a radical reaction because it could break on these ones. For comparison, the OH bond has a bond strength of 464 kilojoules per mole. That's a strong bond. OH bonds do not become involved in radical reactions very frequently. Carbonyl, some of pi and sigma. It's a very strong bond. 774. Again, these figures aren't memorised, but the CBr bond is weak, the OH bond is strong, the carbonyl is strong. You therefore don't need to think too much about OH bonds in radical reactions because of their lability. Okay. So the other huge benefit of these things is that they undergo very regioselective reactions quite often in some of their reactions. So if you're dealing with an unsaturated carbonyl compound, it's an unsaturated carbonyl compound. If I was to treat that with a Grignard reagent, which is a negative reagent, or lithium reagents, I would get a mixture of products. R minus. With a conjugated carbonyl compound, so-called alpha beta. There are two modes of reaction, and you nearly always get a bit of a Dodds-Dinner mixture of the two of them, so they can attack the carbon in what's called a 1,4 reaction. Or you can attack the carbonyl directly in A12. Well, for example, example, vineyards or lithiums. But we actually a mixture of both adducts, which makes these reactions a little bit lacking in utility when it comes to synthesis. The nice thing about radicals, of course, is they undergo a single process. They always add in a 1-4 fashion. We add the alkene at the left-hand end. We do not add to the carbonyl. The reason being, the carbonyl has a strong bond. We don't want to break it. So they are very good in terms of regiostatic reactions with alpha, beta unsaturated carbonyl compounds. And what we'll see in the last lecture is their absolutely crucial synthetic application is they are great at forming rings, but very selectively. So if you take a radical like we've got there, it's called a hexenal radical. 1, 2, 3, 4, 5, 6. That radical can add to either end of that alkene. It adds to the 6th position and get a sigma ring. It adds to the 5th position and get a fiber ring. With radicals, we get what's called the rule of 5. We'll discuss this later. We form a 5-membered ring only. Which is counterintuitive because 6-membered rings are more stable than 5. Radicals give us 500 rings in the hexenal radical system. In contrast to cations, the radicals always give us a 600 ring. So the corresponding cyclization of a cation, 2 electrons this time, that's the cation, and we get the 600 ring. So again, a beautiful example of the benefits of radical reactions. We can control ring size compared to our ionic counterparts. Okay, there's a few examples that I'll go through next time. Well, those of you that have had my lectures before, I always give questions out at the end of each lecture so we'll go up the next time. So my question for this week is as follows. We all today. Right. And these are actually online as well, so there's loads of stuff on Blackboard on last day. There's lots of links, and the questions will be going up along